Next, we have two gentlemen, one who I know quite well, and one who I've never met. Hi. First, and I'm not trying to prioritize you in any kind of favoritism. I'm just going from the top here. First, we have Michael Kluge. He's from Technische Universität Dresden. Michael works at the Center for High Performance Computing at TU Dresden with parallel file systems for more than 10 years now, usually chasing topics like performance analysis and debugging. He currently focuses more on how to design storage systems in the future and on how to make the advantages of big data technologies available to HPC users. Michael coordinates the development of storage concepts for the central IT services of the university and procurements and installation of HPC hardware. Next, we have Johann Peyrard from Atos. Johann Peyrard, System Performance Engineer for HPC at Atos Bull. He has worked on cluster HPC systems for 10 years with primary skills in system integration, development, performance analysis, and debugging. His current role is working on storage solutions for each tender and archiving the specific level of performance needed. Gentlemen, welcome to the show. Come on.
Hi. I will present you the 1 million IOPS TU Dresden file system we have set up for the University of Dresden. So first we had a benchmark tenders which required 1 million IOPS random read. So we had to choose a storage system with the disk, the controller, and the server CPU and memory. We've put this storage system, so the disk, controller, and server, in IO cell, and we've duplicated this IO cell to set up the Lustre file system. So the benchmark tenders. We required with a custom benchmark to get the 1 million IOPS random read. When we set up the system, we achieve 1.3 million IOPS. And to reach this performance, we need 600 nodes with 24 ppm. So it gives more than 14,000 tasks, and it runs for less than 5 minutes, and it gives the score we see above. The storage system we have chosen to reach this performance. So we have used a Toshiba disk because this disk, which are SSD drive, give more than 100 IOPS 4K in random read, and this is the performance the kind of performance we need to reach. We use 60 disks like this, and we put these 60 disks on 3 different shelves to reach this performance. So we have put 20 disks on this EF560 dual controller NetApp. This controller is a EVBridge 6-core controller with 4-port SAS3. Each controller has 24 gig of RAM, and 12 gig are mirrored between the 2 controllers which are on the back of this shelf. So this shelf contains 60 slots. We put only 20 disks on each shelf, and each shelf gave nearly, I think, nearly 400,000 IOPS. So here is how it's made on the 560. You have two motherboards which are linked together by a SAS link, and you have 4 hosts, 4 SAS ports on the top, and the core processor with the data cache. So it's a 6-core EV bridge CPU. You have 3 DIMM of 8 GB of RAM, and 4 SAS ports on the top. And on the 24 GB of RAM, you have 12 GB, which are mirror with the link between the two controllers. So the controller is able, the dual controller system of the NetApp E5560 is able to deliver near 1 million IOPS in random read cache. It delivers more than 100 IOPS in random writes. So the random read is really, really better on this storage controller. The sustained performance is 12 GB in read with big blocks, and 6 GB writes with big blocks. We have chosen to put this server in front for the OSS. It contains 2 EV Bridge CPU, 8-core CPU at 2.6 GHz, and we've put 4 DIMM on by sockets. There is 8 slots, but we've used only 4 DIMM slots because there is 4 memory channel on the processor, and it allows us to have the right bandwidth by sockets. So there is 3 PCI slots by sockets, and we use to set up 1 IB card by socket and 2 SAS cards by sockets. So this OSS is made of 1 EV Bridge socket. So we have 2 sockets, but it's a EV Bridge 8-core. There is 4 DIMM, and there are 3 PCI cards. And we set up the system, so we use 3 PCI cards on a socket and 3 PCI cards on the other socket because it's a dual socket controller. The I/O cell is made of 1 NetApp EF560 you see on the back with controller A and controller B, which are linked by SAS, and 2 servers on the top, which are linked by SAS cable. So there is 4 SAS cable by server which go to the EF560, and 2 IB link which goes to the top. The pattern is 2 server and 1 controller, and we have used 3 patterns for the OSS and 1 pattern for the MDS. So the whole stuff gives this system. And here is the file system which is set up. Michael, it's for you.
Okay. For me, the question was, after Bull succeeded with the benchmark numbers, was how much compute nodes or how much processes do I actually need to get good performance? So we designed a system for our data analytics users that have a few terabytes of data set and want to search around in the data and have random access capabilities, and they have usually not large node numbers. And so I set up a couple of measurements and I want to present some data and insights now. First, what I did, I disabled the read cache on the servers to actually see the performance of the RAID array. And I opened all the files during the tests. So files are always created during tests, and I set some POSIX hints to not have any local caching in the VFS layer. So this is small. It was bigger in my laptop. So I tried to use at least 4x of the size of the server RAM. So we have 6 servers. And whenever I used one LAN, I used 4x of the size of the server and so on. MPI ranks, I tried to rotate between writes and reads. So at the beginning of each benchmark, all the data is written, and then the MPI ranks are rotated so that they have to use, to make sure that they read the data from the disks and not from local cache. All the tests that use many LANs always start at LAN 0, so that it's deterministic. I've collected this data not in exclusive mode. So the numbers presented here are either have error bars or show the maximum of at least 3 measurements. This were quite a couple of runs and would have required for the file system, I think, 4 or 5 days of downtime just to take those measurements, and they wouldn't allow me this. And I always used one individual file per process. So each process on each core would use its own file, because I didn't want to test the metadata server with this, but the RAID array. So if you do random 4K write IOPS on a normal RAID 6 LAN, 8 data disks, 2 parity disks, that's our other scratch file system that we have. So we have 2. We have one NetApp system with 3 terabyte disks and standard SATA disks. That's what we see here. You get like 700 IOPS from one LAN, which is kind of reasonably. If one disk does about 100, and you have 8 disks, so that looks okay for me. So if you wanna get high IOPS, you have to use SSDs, because that just using lots of LANs doesn't work. So if you then take one process and use 4K IOPS on, so the text there is pretty small. Use 4K IOPS from one process and write to one LAN. You end up with about 30,000 IOPS that you can do. If you increase the stripe size, this number will stay. And if you look on the node, you can see that the process writing the data is running at 100% CPU load. So basically, the 30,000 IOPS, or in that case 32,000 maybe, is all that your one core on your Haswell chip can do for you. That's basically, there might be Lustre tunings that help here. I didn't change any setting between the benchmark run and these tests. So the system is still on this benchmark setup. If you are interested in all the LCTL settings that Bill used, we can certainly look this up in the Shine setup file. So 30,000 to 32,000 IOPS for one process. That's what you get from one node. I think that's a reasonable number. So what I then did is utilize all cores and tested all my LANs. So we have, as Johann said, we have 60 SSDs, and each LAN is about, I think, 3.7 terabyte, and it's 5 SSDs per LAN. So that each server exports, so each server pair has one SSD array. Each array has 20, so each server exports 2 LANs in a normal case when you have no failover. What you can see here, if you test a single LAN with 24 processes opening, one file per process on one LAN, you get between 40,000 and 80,000 IOPS. I mean, this is a big performance variation. It's still the best number out of 3-4 runs there. The interesting thing is that the writes are close to their limit. One SSD can 25,000 IOPS, so 5 can at maximum do 125,000 IOPS. And SSDs are faster for reads. Johann has seen 125,000 for one SSD reads. And so a LAN should be able to do something like 600,000. What you can see here, and this is consistent in all my tests, if you end up with like 60,000 IOPS here. So I'm not sure what's the problem here in this test was. I did that at some point later again, and I actually reached like 600,000 IOPS with 4K reads from one stripe. So that's this LAN 0. But you can see for the reads with one stripe, you end up like at 100,000 IOPS on the right side, and with more stripes, you get up to 400,000 IOPS with 24 processes on one node on 60 SSDs. I think this is a nice number to take home. For the reads, you can see that this always starts, if you use one process, it always starts very low. For the reads, for the writes, if you use one process and more than one stripe, there is more performance. There's maybe, I don't know, somewhere a bug. I've seen something on a mailing list about reads being slow. I'm not sure if this is related. I haven't talked to anybody from the Lustre team about those numbers before the conference, so if someone has clues about this, I'm happy to hear about this. So another thing I did is changing the block size from 4K to 1 meg. So 1 meg is what we would usually use for our bandwidths, IOR runs, and I wanted to know what block size do you need to actually see the full bandwidth of the system. So if people say, okay, it's good that you can do 4K IOPS, but I have to actually read all the data. So what is like the optimum block size to saturate the bandwidth? And it seems to be, so the yellow and the blue curve are the same, just that the blue curve I measured in 4K steps, like every number, and the yellow curve I only depicted the powers of 2, and the same with the green and the red curve. And from a bandwidth perspective, something like 128K are the optimum where you can, it's like the smallest block size where you see the full bandwidth. And there are some nice patterns there, probably due to some ratio of or some fixed transmission sizes on LNet, whatever. It's probably a nice task for some student to figure out those patterns. Looks familiar. So if you, so what I did before was either a 100% reads or 100% writes. So what I did here is take 24 processes on one node and then change the mixture between reads and writes, because what we will have at the end is probably people running both or running jobs concurrently on the system. So some will read, some will write, and I wanted to see if they can hurt each other. And actually, it turns out that if you have a write percentage about 80%, then this looks a bit like a sweet spot for the performance. But again, in this picture, we see that for zero, so for reads, which are the left side of the graph, we see 60,000 IOPS. So what I did then is use more nodes. So all the measurements up to now are only one node. This is up to 256 nodes. The cluster in the we purchased has about 1,500 nodes. And what you can see is that with the writes, as you increase the nodes, you are very fast at a really good number, and the number stays, which is good. And for the writes, you see about, I think, the theoretical peak of the SSDs is, I think, 1.2 million IOPS. And what you can see here is that you can get about 800,000 really quick, and then it stays there. What I also did see in the test, that if you do 100% reads, you see something like, I saw something like 6 million or whatever IOPS. So it just jumped through the roof, the number, and I haven't had time to figure out why I suddenly see those numbers that are much bigger than in the procurement. But the benchmark run for the procurement was that we filled the whole 44 terabyte with one data set, so all 14,000 processes, each with a single file, filled up the whole SSD file system, and then we had a 5-minute run. And this is, because it was during production, I couldn't really use so much data, was a couple of terabytes where I run the test on. So there are probably controller caches that come into play, and more things that are worth investigating, and didn't look into this yet. So what to take home? 30,000 IOPS is what a single Haswell core can do for you. Can easily see more than 100,000 IOPS from a node, and this scales well, and the performance is pretty stable. I'm really satisfied and looking forward to maybe next year come back with some user stories. So what we already did is put some not benchmarks, but small user scenarios onto the node, just without any optimizations, just to see how the speed up is. It's now I've seen a factor of 5 to 10, just by throwing the application onto the SSDs and then run. I think there is more to come. Thank you.